AP Chemistry, this is the answers video to day 45. It's the Introduction to Kinetics. It's the first of a 4-lesson set on a very important subject on the AP exam called kinetics. So what does kinetics deal with? Well, I'm not going to answer every question. These are in the video, but I'll answer a few, especially if they're important. What I would like you to see is write all answers as complete sentence answers. That's what you have to get used to doing on the AP exam and really in college level work. So don't just give one sentence or one word answers, even though I might do it here just to speed along, but this one will write a complete sentence. So you would simply write something like this. That would be a satisfactory answer. It deals with the rate or speed of a reaction. You can also write the following. Okay. So kinetics deals with the speed, rate of a reaction. It also deals with the reaction mechanism. That's how a reaction takes place. How do the atoms and molecules actually break apart and recombine to form new substances? Okay, so that would be a typical answer for this. The first sentence would have been satisfactory. Okay, so what is the scientific term for speed? That's rate. And it means the change, delta, change in. So by now, I hope you know that, and let me write the delta so it looks better. A delta in a variable such as the concentration, the molarity concentration of a product or reactant with respect to, that's how you read this, with respect to time. Okay, so again, that's in the video. Are rates positive or negative? They're always positive. What is molarity? Molarity is the concentration in moles per liter. That's just review from when we did solutions. That was very quick, but we will be dealing with solutions quite a bit in the future, okay? So again, I'm just giving the quick answer. You write complete sentence. So it's moles of solute. That's the lemonade powder mix per liters of solution. That's the lemonade powder and the water mixed together. Okay, so that's molarity. It's the most common measure of concentration that we will use in this class. What two variables are involved? Well, what I had in mind was this, either concentration or pressure. Now, a third variable that's involved always is time, change in time. So I'll add that one. What two rates is kinetics interested in? It's kind of the same question. So it would be change in concentration per change in time. And we didn't really deal with pressure, but the way you would deal with pressure of a particular reactant or product would be P subscript A. So if that A is the reactant, that would be PA. So change in pressure with respect to change in time. Okay. So number 7 is kind of asking the same question again. Change in pressure or concentration with respect to a change in time. Just trying to reinforce that concept. So it's how fast either the pressure or the concentration is changing. If it's a reactant, then the concentration would be going down. If it's a product, something on the right side of the arrow, the concentration would be going up. Okay. Write the rate expression for this. So the rate expression would be, okay, let's look at number 9. Write a rate expression for the reactions 2A produces A2, a molecule of A2. So this is covered in the video right around 13 minutes, a little after 13 minutes. But let's go ahead and do it here. It's a little confusing with the negative signs. So this is a reactant. That means it's decreasing. And so there's an implied negative sign there because it's decreasing. Okay, so you could write this as negative delta concentration of 2A. And at one point in the video, I showed the negative sign inside. Again, it's not, you normally don't write that negative sign. It's just since it is a reactant, you know that it's decreasing. And it's per change in time. Okay. And then over here, you have, it's positive, it's increasing. So it's the change in, positive change, and I'll just put a plus sign to emphasize that. You normally wouldn't write that. Concentration of this A2 per change in time. And the change in time has to be the same in both cases. It could be 1 second, it could be 1 minute, it could be 3.5 minutes, whatever it is. This is used up in the same amount of time that this is used up. So a rate expression equates these two, and the reason we do that is so that we can figure out the rate of change of one of the reactants or products in relation to one of the others. So what we're going to do is, if we want these two, this is being used up twice as fast as this is being produced. And this is a positive and this is a negative. So what you simply do is you take this coefficient here and you put it out in front. Since it's a reactant, you put a negative sign there. And now I'm not going to write the negative sign here, but it's all of this here. So it's that times delta concentration of 2A, and that's going to be a negative number since it's negative, so there's an implied negative sign there, over delta T equals, and the coefficient here is 1. You don't have to write it, but we'll write it just so we understand that there is a coefficient there. It's 1, and it's positive because it's increasing. And that's going to be delta concentration of A2 also over delta T. Okay, this will make more sense when you see a couple of the numeric examples that I'll do and then on the next page, okay? But that would be the rate expression. So since this is being used up twice as fast as this is being produced, if you want these two to be equal, if you want that to be an equal sign, then you have to cut this number in half and put a negative sign on front because it is decreasing to make it equal to the rate that is being produced. Okay, so let's write the rate expression for the following reaction. So it's simply going to be this. Now notice these are all equal signs in between everything here. Now we're going over to the product side, so everything's going to be positive. And let me just clarify, these are the coefficients. So they're the numbers that go out front, and these could just be either single elements or compounds. Okay, it could be CO2, H2O, or it could just be an element like silver, for example. Okay, and the small letters are the coefficients. So you simply take the reciprocal of the coefficient. Again, don't get too deep into why this works. Just learn how to mechanically do this, put this together. And it's the negative reciprocal of the coefficient. It's negative on the reactant side. It's positive on the product side. And there's equal signs between all of them. So you can equate any rate of any product or reactant with the rate of any other product or reactant and therefore solve some problems. Okay? All right. And this was supposed to be BrO3 minus. I don't think I put the minus signs that were in the video. I just think they confuse things. So I'm asking you, it is 1 BrO3. Okay, so again, 13 is straight out of the video. Let's go ahead and I'll do some of these and you do the rest, okay? So this is a coefficient of 1. I do like to write coefficients of 1 to imply that there is a relationship. There's 5 times as much of the bromine being used up as of this compound right here, and there's, you know, these give relationships of how much is being used. So I do like to write the ones there. Okay, so for this one, it's going to be a negative because it's a reactant. So negative reciprocal of 1. And I do like to put these in big parentheses. You can do that as you wish. It's changing not BrO3, but the concentration of BrO3. Remember, that's a molarity. That's moles per liter. It's not just moles of BrO3. And again, I'm omitting the negative signs, the ion signs. In other words, they just, I think, muddy the waters here. Remember, whatever delta T is, it's the same for everything. Okay. Now, I might have been a little smarter to start this way over here. It's going to be pretty long. And I'm going to leave this one for you to do. So that's going to be equal this. I'm going to put that, and then I'm going to leave a space there. And then I'm going to do this on the product side. So this one's going to be positive. It's a positive 1 over 3. Again, the plus sign just to emphasize that. You don't have to write that. And then finally, this last one you're going to put right there. This one you're going to put right there. So I'm going to leave those two for you to do. Okay. All right. All right. Now we get some with some numbers. So you'll see where does this become useful. All right. So it wants to say if the consumption, that means it's being used up. Get used to words like that, okay? Consumption of this, BrO3, equals, now they give you a specific number. What is the rate of formation of H2O? Okay, so, well, I'm going to have to write this one since we need that. So it's going to go ahead and be 1/3. Okay, so we're interested in just this one specifically and this one here. So I'm going to come over here, and I am going to write it way over on the side this time. So it's negative, again, write 101, 1 over 1 as you wish, of this. Okay, so they're giving you this number right here, okay, right there. So what you can do is go ahead and plug that number in here. So this is just -1, we'll just call it -1 times this. So you notice that the negative is because it is a reactant, it's being used up, so the negative is going to become a positive. Okay, so now it just becomes an algebra problem. You have a 1/3 here. You want to isolate this. This is what you're trying to find out. You're trying to find out the rate of formation. That means it's with respect to time. It has a time element there. Okay, and so we're going to multiply this side by 3. And over here, I'll sneak it in here, this side by 3. Multiply both sides by 3, so the 1/3 and the 3 cancel out. So you've isolated the variable. You know, if this looks kind of muddled and confusing, just replace this temporarily with variable x. Okay, so it's 1/3 x equals this number, and then just solve it. All right, so now it's 3 times, forget the -1, okay, but it's there. So it's 3 times -1 times -1.5. You multiply all that together, you get positive 4.5 times 10 to the -2. Okay, and it's a rate, so it's molarity per second. That's the unit of measure, okay? Molarity per second. That's how fast it's happening. And that equals this rate over here. And that's your answer. That's all there is to that, okay? Seems like a confusing problem, but then, you know, it's not that bad. Okay, let's do these together. A lot of students ask me about these in the last couple of days. Let's just do them together. So let's write the complete rate expression for that. Okay, so that's everything. Negatives on the reactant side, positive on the product side. Everything, though, is an equal sign, okay? No plus signs, no arrows. Everything's equated to each other. Those things are all happening in the same amount of time, okay? And again, there's implied negative signs here and here. So when you multiply by a negative coefficient like that, it becomes a positive number. Rates always have to be positive, okay? Write this down just one time. I don't think I asked you to write it anywhere else. Because time always only moves forward. Boom. Okay, just write that once. Okay, let's go ahead and do these together, all right? So what is rate of consumption of O2? If that is the rate of consumption of O2, what is the rate of production of CO2? So we're only interested, close my parentheses here, we're only interested in this one and this one. So we simply write those two down here. And I'm a big believer in always writing the general formula first before you plug in the numbers. Okay, so that's the relationship we're interested in right there. And now we know a value for this. Save space. We know our answer is a rate. It's going to be molarity per second. So I'm going to omit those, so it just kind of clutters things up. I usually believe you should always write your units of measure, but here I'll omit that. Okay. And we should have written this as a negative up here and up here as well. because it is being consumed. So there's always that implied negative sign, okay? So that we're going to kind of sneak that in there, all right? And then this is going to be okay. And if you get confused about the negative sign, should it be there, should not, just remember the rate at the end always has to be a positive number right there. Rate always has to be positive. Okay, now it's just an algebra problem. If you want, if you want, you can write it like this. I'm going to use up all my space here, but you could write it like this. Okay, you just have some substitute variables that are simpler than all this stuff here. Okay, or in fact, you know what x is, so you can put that number in there and just call that y. But that's not, again, you'll get used to this, just seeing these, and it won't seem like that's really necessary. What we're going to do, though, on both sides, we're going to multiply. We need to isolate this. This is what we're looking for, the rate of production of CO2. So we're going to multiply by 3, just like we did on the last problem. Come over here and put a 3 there, and I'll close that. So it's negative. It's going to be negative 3/5. Okay, you can see that. Negative 3/5 times negative 4/6. So do that on your calculator. You get this positive number. Remember, when you have scientific notation numbers and non-scientific, you treat these just as coefficients, okay? So you only multiply the 4.6 that, and do that, and then 4.6. That's going to stay the same as long as that's a number between 1 and 9.999. Remember that rule? That's a number, that we don't have to adjust the decimal. So that means that exponent's going to stay the same. Okay, and that equals this, what we were looking for. How fast the concentration or the production of CO2 is taking place. Okay, and that's your final answer. All right. Okay. Let's go ahead and do 17 together. All right, so now it's the propane, and that's being consumed. It's on the reactant side, and that's an error. So that should have been. No one asked me about that, and I should have caught it. So that O2 is going to become C3H8. What is the rate of production of H2O? Okay? So if that threw you off, you had a right to be thrown off. That should have been corrected earlier. Okay? All right, so let's go ahead and do that. So the propane is this one right here. And I did not give myself enough space. I'll sneak that in there. H2O, so we're way over here now. It's that one. Okay, now we'll come over here and plug in numbers. And I'm just going to stick a negative sign now. I don't think we need to write -1/1 anymore. Okay, and it gives you that number right there. Okay, so, and remember that's a negative number because it's being consumed. There's an implied negative sign there when it says it's being consumed. Once again, I will not write the units of measure because they just muddy everything, and I should have written them up here, by the way. Molarity per second. Okay, molarity is the concentration, time is in seconds. Okay, M over S. All right, and that's going to equal. Okay, so what do we do here? Well, you can get rid of the negative signs for one thing. The other thing is you multiply both sides by 4 and by 4. So this becomes 4 times positive 8.9. It's pretty close to 36. 35.6. These canceled, of course. Okay, there's your answer. The only thing you need to do is adjust the decimal. So we're going to make this number smaller. This goes way back to lesson 2 of Unit 1 of Foundations. So we made this number smaller. We have to make this number bigger. Negative exponent getting bigger, it moves it in the positive direction. So it's 10 to the -2. And now that we're at the end of our problem, that's a 2. We're going to put molarity per second equals this. Okay. And there's our final answer, okay? 3.56 times 10 to the negative 2 molar per second is the way you would read that. Okay, and there's the answers to 18 and 19. I'll let you work those out, but there's the answers that you should arrive at. If you think I'm wrong, let me know. All right, number 20, what is the kinetics rate law? So that's straight out of the video, but it's basically the law. The kinetics rate law is the law that will tell you at a specific moment in time how fast will the reaction be going based on three things: the rate constant K and what the concentrations of the reactants are. Okay, so let's go ahead and write that out, all right? Okay, so what is kinetics rate law? The kinetics rate law, I'll just write it out. Okay, so let's read this. The kinetics rate law gives the rate, the speed of a chemical reaction based on the concentration of the reactants. That's key. It's only the reactants, not the product. So only this side of this reaction, for example, is involved in the rate law, not the product side. And the rate constant K, which we'll talk about, but K is essentially works temperature in. Chemical reactions, by and large, move faster or happen faster at a faster rate when the temperature is higher, because the molecules or atoms collide faster and harder, and therefore the reaction happens faster. Okay, so that's it. So let's write the rate law for this. Okay, and it's very simply going to be this. The rate, meaning the rate of the reaction, okay, so the rate equals the rate constant. Okay, so this is called the rate constant. Times the concentration of reactant A raised to some power, X, and B, concentration of B, raised to some power Y. So once you have this equation, if you know your rate constant and you know what the concentrations of A and B are and what X and Y are, you can tell how fast the reaction is moving in molarity per second. How many moles per liter per second? Okay, molarity per second. Okay, so this is the rate constant. Okay, so rate constant, so let's go ahead and write this: K, X, and Y. Okay, so K, X, and Y are determined experimentally, and that's what we're going to do in the next lesson. They are not the coefficients, A and B. Okay, that's a common mistake. They are not A and B up there. All right, so we're going to go ahead and do some of this. Does the product side of the equation play a role in the rate law? So I just answered that, but again, watch the video. I don't want to give you all the answers here. I want you to be watching the video. How are the exponents X and Y determined? Just said that. What name is given to K? It's called the rate constant. What is the order of the reactant? Okay, so the order of the reactant is the exponent to which it's raised. So in this case, the order of A, and again, I want you to write these as complete sentence answers. You got to get used to doing that. So the order of A is 2. I'm just giving you the number. The order of B is 3. The order of C is 0. What is the order of the overall reaction? So in that case, you would add them. 2 plus 3 plus 0 is 5. Okay, what are the units of a reactant expressed A or B? Okay, it's molarity per second, so it's M over S. Okay, for either one of those. That's what that square bracket means. The square bracket means the molarity. So I should actually say it's just molarity. I should take out the seconds. That's purely molarity. Okay. Okay, the rate constant is a function of what variable? That I want to be sure you know that it's temperature. Generally speaking, not always. Generally, the hotter the reaction, the faster it moves. Okay. How does the concentration of a zero-order reactant affect the rate of the reaction? Okay, it doesn't. Okay, it doesn't. You can increase or decrease the concentration of a zero-order reactant, and it won't change the speed or the rate of the reaction. So I'm going to say it doesn't. Again, you're writing complete sentence answers. How does the concentration of a first-order reactant affect the rate of the reaction? Rather than give you a math-type sounding statement, let's just give an example. So doubling. I could be tripling. I could be quadrupling. You could change those words. So doubling. Okay, so doubling a first-order reactant doubles the rate of the reaction. If you tripled the first-order reactant, it would triple the rate of the reaction. It goes up proportionally, directly proportionally, okay? How does the concentration of a second-order reactant affect the rate of the reaction? Again, let me give an example. Okay, so if the concentration is 2, let's just pick a number. You're going to square that. That's what second order means, is you squared it. So it's going to be 4 times faster. Okay? So it squares it. It basically squares it. So I just gave an example. Doubling a second order reactant quadruples the rate of the reaction. Okay? Alright. So how is the rate of the following affected? So here's an example. K is just raised to the first power. So if you double K, you double, comma, double the rate of the reaction, okay? Multiply that. If that's times 1, then you have a certain number for rate. If you make that a 2, you double that number, it makes it 2 times that number, okay? Doubling A. Now that's second order. So doubling A quadruples. That means 4 times, okay? You should know that word. 4 times the rate of the reaction, okay? So if that number is 1, then you have a certain number here. If you change that, so 1 squared is 1, right? If you change that to a 2, then 2 squared is 4. So it goes from, the whole rate goes from 1, whatever that number was, times 1, to whatever that number is times 4. You made it 4 times greater, okay? Again, if that was a 1, 1 squared is 1. If you change that to a 2, you double that. Then that's 2 squared is 4. So all of a sudden this number, instead of being a 1, becomes a 4. All right, and finally doubling B, it's first order, so it's going to double. All right, that takes care of this. And so get this done. We need to get these done. You need to keep up from now on. This is not something you can fall weeks behind anymore on these lessons. All right, so if you have any questions, come to tutoring, and I'll be glad to help you. All right, we'll see you in the next lesson.